So, without further ado, Dr. Haaland.
Kevin, you're not an easy act to follow, so I look at this as an opportunity. I think the three gentlemen up here, Kevin, Gary, and Dick, could probably as easily have given this next talk as myself. So I like to think of that as I've got lots of good backup here. I have strayed from an original career in space physics and have focused more on the upper atmosphere, so I'm reaching back in some cobwebs here. Let me describe for you very briefly how myself and the next two speakers approached this conversation that we're starting here. We thought it would be great, a good idea, if everybody here could take away something that allowed them to have a better, more informed conversation with other citizens about climate change. And so we kind of gravitated towards areas that we felt most comfortable with. And so the theme is we're going to teach you, we've each chosen, and my colleagues can correct me if I'm wrong, we've each chosen 3 misconceptions about climate change. They're fairly common. You can find them everywhere. Maybe you've heard them in conversation. We've chosen misconceptions that we probably have leveraged our interests and our expertise a little bit, so that's why we're talking about the topics we are talking about. And then thematically, we're kind of working our way out from the big picture down to the local picture. And I think the local picture is going to be more important for you to walk away with today because it's the more actionable items that you can have. I'm going to talk about the sun and its impact on our climate change and some misconceptions about solar variability and how it influences climate. There's not much we can do about the sun. I'll be the first to admit that. Professor White down here could talk for a lot on the fate of the sun. We're not going to worry about that so much here. So that's our agenda for this afternoon. And again, we wanted to, rather than to complement Kevin's talk, we thought it would be great if we could talk about 3 common myths and then bring them down to you to help you walk away from here today with some ideas that could help inform your conversations with other people who aren't here. Overall, we're going to talk about impacts and adaptations. Again, I can't promise any adaptations with the sun because we're not going to control that. And then hopefully we'll have plenty of time for discussion and questions. And I'm looking to one of my colleagues to help me stay on time. Anyway, I'm sure Gary will get the hook for me. Thank you. All right, good. All right, so I chose to address this misconception. In yellow here, I've got this fairly a common misconception about climate change, and one of them is that variation in solar activity can account, or solar output can account for and is responsible for warming of the climate. And that is a myth. I think it's important for you to understand that everything we're going to talk about today is a myth, and then we're going to hopefully have you leave here with the correct understanding of that. To do that, we're going to have to do a little bit of science, and I apologize for that. We are, after all, physics or lecturers in our various fields, so we can't resist that opportunity. And I chose to go about addressing this misconception by explaining to you a little bit about how our sun works, or at least our current understanding of how the sun works. And then go out from there to address what we've observed, how the Earth interacts with our sun, and then try to tie connections to that interaction to climate, okay? And then give you some evidence that will hopefully help dispel this. Again, the yellow box is a misconception. We want to fix that. That's our goal today. Caveat, we can't be exhaustive in our support and evidence for these claims, so we've had to choose perhaps a subset of the evidence that's out there. Kevin alluded to the fact that some of the data is highly variable. We are fully aware of that, and so again, we could discuss for hours some of these things, and we won't. We're going to give you some of the salient points there. I want to talk about the sun, though, and its activity as a starting point for this conversation and dispelling this myth. Here's where I should really turn the stage over to Dick, former professor of astronomy. Our sun is basically a middle-aged yellow dwarf star who will eventually end its life as a white dwarf. Is that true? Yeah. And that's going to be a catastrophic end for most of the solar system, but thankfully we've got a few billion years before we have to worry about that. So let's focus on the current situation for the sun. It's powered by fusion, so we have helium or hydrogen being fused into helium at the core, and that's a huge source of energy that keeps the sun supplying the Earth with energy. Light is the primary product of that we see. The upper atmosphere of the sun is very hot. It's a plasma. It's basically overall electrically neutral, but it's so hot that the hydrogen has separated into protons and electrons. There are a few helium nuclei there, lots of electrons again. And it's so hot and those individual particles are so energetic that the gravitational pull of the sun is unable to keep them in place. And so they escape the solar atmosphere and leave the sun and bathe the solar system in this wind of protons and electrons and a few other heavy elements and some helium nuclei. That escaping atmosphere is what we call the solar wind. It is basically, if you look at the picture up there, the flow that's coming out from the outside of the obvious disk of the sun itself. It's variations in that ejection of mass from the sun that creates variation in the sun's output, both from a particular standpoint and from a light standpoint, and that's where I'm going to focus some of my conversation in the next few minutes here. So that's our sun. Solar wind it's not a wind like we would experience if we were to go outside today and feel a breeze on our face. It is, again, a plasma, which is a very hot gas that's electrically neutral, but because you have lots of conducting electrons and protons in there that can conduct electricity, they're connected electrically. It makes for some fabulous physics problems because you get to combine electricity and magnetism and fluid dynamics all in one go. It's a very complex problem. The point is, if you look at the picture up there, the flow rate, the flow speeds, if you will, of that plasma coming from the sun is highly variable. And that is due to, again, conditions on the sun itself. We kind of think of the sun as having its own weather system, and that is it has its own magnetic field, and that magnetic field also permeates out into space, in part carried by this conducting plasma of the solar wind. But basically it bathes the whole solar system in this flow of particles, not just light, but particles that have mass and have definable speeds. If you think about this, it's a little bit interesting because light is a photon. It travels out in pretty much straight lines as it comes from the sun out to planet Earth. But then these particles with mass, protons and electrons, are being spewed out of the atmosphere of the sun while it rotates. And so if you look at the picture in the lower right corner, one way to think of the sun approximately is one of those 2 or 3 handled sprinkler heads where the water is flowing out in chunks and moving in a circle. And it's the magnetic field of the sun and this variable flow that creates these areas of higher flow and less flow. And then we have to plop our Earth somewhere in the middle of that, and we see those variations in the flow of charged particles. The important point here, though, is that the solar system, and Earth in particular is part of that, is not part of a constant system. We look out the sun every day. If it's bright and sunny, we think, well, the sun is just as bright as it was yesterday, and that's not quite the case. Because of the particle nature, because there are other optical or light radiation aspects to the sun's output as well. And that's what we want to focus on here for the next couple of minutes. So as I mentioned before, we're not just bathed in light from the sun, but we're also bathed in particles. And it's this output from the sun that allows us to measure how variable the output from the sun actually is. And so there are a number of ways that we observe these variations, and I want to highlight a few of those. The first thing is we're one of the few planets to have remaining a strong enough magnetic field due to stuff going on inside the core of our planet. And this magnetic field is important because it creates a buffer, if you will, for these charged particles. It's very good that the light gets in so we can see during the day and grow crops. But we don't want the ionizing radiation of very high energy protons and electrons streaming down to Earth. So what this magnetic field does, the Earth's magnetic field, is it causes the particles to be turned and actually flow around the front side of the Earth. Those moving charged particles create what physicists like to call currents, and those currents create their own magnetic fields, and those are measurable. And that's one way that we determine how active the sun is. A pulse of charge comes out from the sun, it interacts with the Earth's magnetic field, those charged particles get turned, and they create a secondary magnetic field, and we can actually measure that on the surface of the Earth. Other ways to monitor the variation in the sun's output is to look at the aurora. That's where I started my space physics career, was looking at the aurora borealis, and it's a very visual reminder that the sun's output is not constant. Unfortunately, you have to go fairly far north to see that on a regular basis, and it's very difficult to quantify solar activity from auroral activity, but we have done it. There are all sorts of indices that we can measure. Again, optical signatures and magnetic signatures. Another thing that we use to measure solar variability is the number of sunspots. We've been measuring sunspots for quite a long time, since the first time we trained a telescope to look at the sun, and we realized that those little spots were not just specks of dust on the lens. So we have been keeping track of the sunspot number, which is literally just counting them and documenting their position for quite a long time. You'll see how long in just a second. And then, of course, we've been able to measure the sun's output directly with spacecraft, and that kind of started in the late 70s, where we've been flying satellites to look at the sun and measure directly the output of light and particles from the sun itself. That's still a tricky business. You know, satellites are pretty small, and space is a pretty hostile place, so to get a consistent, well-calibrated measurement up there is not an easy task. So again, we have, to summarize, we have a sun that offers variable output. We have ways to measure that variability. Okay, we're gonna look at a couple of those in particular. So the sun's outputting light, obviously, it's outputting particles. Let's focus a little bit on the light aspect of that. The sun, as we all probably gleaned, is the primary source of energy driving our planet. So if you look at this curve here, and I perhaps overused this, two things really I like to look at. First of all, the yellow shaded part is what reaches the top of the atmosphere. This is called spectral irradiance. It shows us, as a function of wavelength, where the energy is coming from the sun. And so you see most of it there is in that visible range, right in the center, right at the peak of that radiance curve. Next to that curve is a model black line, and for those physicists and geeks in the room, the fit of that line to that data is quite extraordinary, and that's a moment in physics that's pretty profound. But then you see the red curve, and that is what actually reaches the surface of the Earth. And so the difference between the yellow and the red is what really drives the heat engine that is our climate, okay? And that's due to the sun. You'll notice a couple other things on there, the wiggles that are due to different atmospheric constituents. So we have the greenhouse gases in there that are preferentially absorbing some of that heat, causing that heat engine to churn about. Different atmospheric constituents absorb in different wavelengths, and that's why carbon dioxide is such an important component of climate change and global warming. But here's a key point. A more active sun, more sunspots is one measure of that, is going to emit more light in the ultraviolet. So while we think of the sun and look at it, you would say, well, it's got lots of black sunspots on it. It's darker, that's true, but when it's more active, it's actually emitting more light in the ultraviolet, which is our higher energy photons. Okay, so there are lots of ways, as I've alluded to, of measuring that solar activity. I don't expect you to read the numbers on the right-hand chart there, But there's a couple of things to take away from that. First of all, the one with the most historical set of data points is the sunspot record, which goes back quite a ways, as I promised before. You notice a couple of other things, that there is a definite periodicity to all of those. And the periodicity mostly is common between all of those observations. And so what I want to point out is that those are all ways that we could look at the solar variability, the solar irradiance variability. And what I'm going to focus on for the rest of this talk is the sunspot number, because it goes back quite a number of ways, and it has probably, it's an easier thing for us to get a grasp on and to actually measure. Okay, so sunspots are an indicator, a metric, if you will, of solar activity. That periodicity that we see here is an 11-year cycle called the sunspot cycle. And we know that very well from lots of historical records. As I mentioned before, when the sun is more active, these darker spots have indicate a reduced output in the visible part of the spectrum, but more output in the ultraviolet part of the spectrum, which is to the left of that peak. And so I've shown you a picture there where you see sunspots on the left in the visible, and then the very hot spots on the right in the ultraviolet picture there. And that's just telling you that the sun is not cooler when when there are lots of sunspots. It's actually emitting more energy, just in a different part of the electromagnetic spectrum. So it's the solar irradiance that we're claiming is part of this 11-year cycle that we're going to use to tie to this myth. And I'm coming back to it, I promise. Here's about 400 years of sunspot data garnered from various sources over time. Interestingly, the red checks are inferred from indirect measurements of sunspot. There was a Maunder minimum way back when that would correspond to an ice age. The more recent solar maxes, we actually count them, and so cycle 24 is in 2015. We're actually on the downside of the most recent solar maximum. It's one of the most inactive solar maximums we've seen on record. But the point is this: if the solar irradiance changes with this periodicity, then there should be some connection that we can observe in climate change, if the sun is causing the climate to change. So you ready for the reveal? Here it is. This is typical of a professor, right? You don't tell people where you want to go, you just lead them there, and that's bad form. Anyway, I apologize for that. So, two things on this graph. First of all, you have the lower blue line, and it's harder to see the solar variability, but it's a sunspot number and an 11-year average. And you see, in fact, that the top red trace is temperature, and it's going up. And you can see some of the 11-year solar cycle on both traces. If you look at the sunspot number on the blue trace on the bottom, it's actually flat, and some would argue that the sun temperature is actually cooling. So if there's anything, we have a hotter atmospheric temperature and a lower sun temperature, and its implication is that the sun is not causing our climate to warm up. So something else must be doing it, and we've heard a lot of good arguments for what that might be today. All right, I think there are other things we could talk about. Radiative forcings in addition to the sun. I've got one last slide here to put the solar forcing component in perspective with other things, and that would be other anthropogenic sources. And we see down here at the bottom, the net solar radiance radiative forcing is very, very small compared to all the other things that Kevin spoke about that are anthropogenic in nature. So I think with that, remember, the myth is that variations in solar output are causing our temperature change. In fact, we saw that there is an anti-correlation, if you will, between solar output and this increase in temperature. And I think with that, I'll answer a couple of questions and then let my next colleague speak.
Yeah, I think we'll save questions. When we have the panel up here, you can ask questions about the sun and or whatever. So I think we'll keep moving along because, as I said, my goal is to get ahead of schedule and have more time for the panel discussion. So the next speaker of these three is Dr. Gary Gianniny. He's the professor in the Department of Geosciences and chair? And chair. He has a master's and PhD in geology from the University of Wisconsin. Prior to joining Fort Lewis, he was an assistant professor at Bucknell University. His research focuses on sedimentary geology associated with aquifers and oil and gas, climate change, water issues, and other related topics in the southwestern United States. His work with students can be found in peer-reviewed publications and in numerous national conference proceedings for the Geological Society of America, the American Association of Petroleum Geologists, and the Ecological Society of America. Dr. Gianniny was the 2012 Fort Lewis College Scholar of the Year, and he's past president and vice president of the Four Corners Geological Society, and he serves as president of that organization's foundation board, I guess. So, Gary.
All right, thanks. See, is this, thank you. Is this roaming mic thing kind of working? Good. I like to be able to see my slides with you, so I might stand back here with you and walk around a little bit. So I'm going to try to give you a little bit different perspective than we've heard because my specialty is really in the deep history of the Earth. And when we see what's going on the planet now, some folks like to say, climate's changed before, that's not such a big deal. And in fact, I want to convince you that it is a big deal and can be a big deal, but it's also an inherent part of our planet. So I want to walk you through some of the history of climate change, and then hopefully that'll put in perspective what we're seeing today. So, so let's go ahead and do that. Let's see if this thing will work. Maybe not. Oh, there. Let me go back. This is awesome. Just a minute. Great thing about teaching every day is you're used to these things. Okay, so so first I'm going to I want to remind you that in science today we just have an astonishing amount of data, and it is phenomenal to be able to understand the planet the way we do. And that's true for looking at modern climate dynamics, and there's a lot that we don't understand, but there's an amazing amount we do understand, and amazing analytical techniques to make sense of that data. And part of the way to think about that is the amazing things we can do with technology now. The computers you carry around in your pocket. All of that's based on science that started in the laboratory. That's the same kind of science that we apply to trying to understand the planet. So I want to talk to you about really different states that we have on our planet and that we've had on our planet. And there are times like now when we have icehouse climates where we have glaciers build up in northern and southern hemispheres and at high altitude locations that build down to lower locations when we have slightly colder climates, really just a degree or two colder. And then we have times in our planet when we don't have any glaciers on the whole place. And those haven't happened in over 50 million years, but we're going to explore some of those. When we do have, one of the things we see in deep time is that there is a correlation between greenhouse gas concentrations, especially CO2, and climate. So we know that we can look at modern ice cores that really take us back 650,000 years, but we can also look back 300 million years and see relationships between greenhouse gas concentration and climate. In that long, deep view, some of the sources of CO2 that have shown up repeatedly really come from the Earth, which in the main source there is volcanism. And we now live in a time where humans have gotten to compete with volcanism and the decay of organic things. And then in deep time, things that are important as well are places where carbon gets stored, and then that's carbon that can't be available or that isn't available for CO2 in the atmosphere and in the oceans. Sinks like that are things like coal. And there's one of the geologic periods that's called the Carboniferous. And that's really a time when we had a tremendous amount of coal deposited on the Earth. Much of the coal you find in the Appalachians and in northern Russia and in Europe is from that time. And as it turns out, weathering rocks, when we have mountains uplifted because plates collide, where those rocks are uplifted, they interact with the atmosphere, and as they get transported to the ocean or into where sediments reside, they actually capture carbon from the atmosphere and hold it in a solid state so that it isn't available to be in the atmosphere. One more thing is oceanic sediments also can capture carbon in a couple different ways, either as organic material directly or in limestones, which are made of calcium carbonate. That's an O3 on the end. So there are a lot of important sinks that have been important in Earth history. And then I also want to tell you about some deadly transitions. Times when we had very rapid climate change. In fact, the biggest extinction in the history of the Earth, we've found out in the last decade, is really related to a time of intense volcanism and very high CO2 warming, or CO2 concentrations, secondary warming, and a massive loss of life on the planet. And finally, this is all in like 12 minutes, right? I'm going to do this. We're totally going to do this in 12 minutes. We're going to look at some of the differences now that we've heard Kevin and mostly Kevin allude to changes in the cryosphere, the ice part of our planet, and what that means for sea level change. I've studied sea level change for a while. I guess it's about 25 years. Usually I think about it and how it affects the distribution of sediments. So in this slide, I hope you can see there are 3 red circles, and I want to talk to you about those 3 red circles. One is a previous ice house that we had here in this region, and actually on the whole planet. And this graph has geologic time. Is this thing a pointer? I think it's a pointer. Anyway, geologic time is on the vertical axis, and the line that goes back and forth is indicating temperature. And on the left-hand side of that graph is where it's been especially warm. That's 25 degrees centigrade. And you can see it drops down to 10, which is probably on the extreme end of things over here. So the first one I want to talk about is this one that says previous ice house. Then we'll talk about a greenhouse time. And then finally the ice house that we are living in. Here's a reconstruction of our planet from about 306 million years ago from my colleague Ron Blakey, who used to be at NAU. But there are some really interesting things to see here. This is what the Earth looked like the last time we had a major ice age, and this is really a period of millions of years of on and off glaciations. Note that there's the equator is right there in the middle of the globe, and that red star is actually about over the Grand Canyon. I didn't put it right over Durango because I wanted us, but you can see actually you can just barely make out, and most people don't know this, but 300 million years ago, the states of the United States were already formed. Or not. Okay, anyway, those are just for reference. You can see Utah has been here a long time. Anyway, we're right there. So there are, and one thing that you should be sure to note, but it's kind of on the bottom of your screen, is that the southern end of the continents were glaciated at this time. And those glaciers waxed and waned with some orbital variations on the order of every 20 to 40 or 100,000 years. And that changed sea level. But it was a system that sort of stayed within that oscillating variability. Note that there's a huge mountain range that goes across the middle of this supercontinent Pangaea. So I mentioned that weathering is a really important way to sequester carbon. And there are a lot of floodplains coming out of those continents where coal was deposited. And these light areas are very shallow seaways where some of the continents were flooded and limestones were deposited. So a lot of carbon was sequestered from the atmosphere. So much so that the relative concentration of oxygen was actually increased from today's percentages of around 21% to up possibly as high as 30 to 35%. As a result, I should have put in my giant dragonfly picture, but insects got really, really large. We have millipede tracks in southern Utah that are this wide, and if you extrapolate that out to a body size, it's about 3 meters long. It's a disturbing idea. Anyway, so that's sort of setting this stage for this previous climate. There's that glaciate. And if you drive up towards Purgatory, you can see deposits from this part of life, from this part of the planet's history on the cliffs just above town. And my colleague Kim Miskell-Gerhardt, who some of you may know, who's here in town, and Scott Ritter and I, who's at BYU, studied these. The yellow parts and orange parts are where sea levels were low. The blue parts in those vertical, these are diagrams, these are where we actually measured the thickness of these strata. And where you see the blue parts, that's where we actually had high stands of sea level here. So even in this cliff here that's across from the electrolyte lake turnoff, you can see that there are 4 to 5 large variations in sea level caused by changes in climate on the southern pole. So pretty cool. There's this history of climate change on the planet. This is a very messy graph from Beaker et al. In 2010, but it takes us through looking at concentrations and proxies for concentrations of carbon dioxide through the last 450 million years of Earth history. It's kind of a mess, huh? Let's look at the bottom one for a minute. Where you see the big dark areas is where we have continental glaciation. And how high those black bars are right here shows you how far in latitude they went south. So this is the equator at 0. This is 90 degrees, the poles. And so during this earlier ice house and during the one we live in now, glaciation went all the way down into the 40s. Think Chicago. Could be a windy thought. Okay, and then in the top graph, going across here, so this is geologic time, are proxies for how much carbon dioxide we had. And there are a lot of different ways to get at that. In this particular paper by Beaker, they're trying to use soil-derived limestone, soil-derived, we call it soil form, that's pedogenic carbonate. And the big thing to watch are the black dots on here and the green part of this graph. And that's actually another way to estimate CO2 variation. That's stomatal density. Plants breathe through holes in their leaves called stomata. And as you probably know, in photosynthesis, plants take in carbon dioxide. When there's less carbon dioxide available, plants will actually increase the number of stomata they have on their leaves. When there's a lot of carbon dioxide available, they reduce the amount. We can actually have modern plants do that in the laboratory. When we use species which are similar to the ones that were alive at that time, they do that as well. So we can use stomatal density as another way to get at a proxy for what CO2 levels were. So in this previous ice house, where you see this flat part of the green curve, we had concentrations which are comparable to today's variation that we see, which are somewhere between 200 and 300 parts per million. And you think you heard Kevin throw that number around. Later in the graph, during this time called the Mesozoic, we get numerous indications that CO2 levels were around 1,000 parts per million. And then if you look at the very end of this graph, where we're going to go later in the talk, we have been back for the last several million years between about 200 and 300 parts per million. 180 to 300 has been the natural variation. Okay, so that's sort of what was going on in the last period of Earth history where we had glaciers. As we came out of that, we had an exceptional experiment in Earth climate that was driven by large-scale volcanism in Siberia. And we now have just astonishing capabilities to figure out how quickly things happened in the geologic past. In this case, it looks like in less than 2,000 years, we had a big surge in CO2 from volcanic activity. And that increased temperature and aridity, and kind of like what we're seeing, like we saw at the end of Kevin's talk, there were very widespread wildfires, evidence of increased erosion, and ocean eutrophication. That's like when ponds turn green and stink really badly. That's eutrophication. And so these are actual pieces of charcoal that are in sediments from this, just after this extinction. So instead of showing you fires in California today, I'm showing you fires from the biggest extinction in the history of the world from 252 million years ago that is associated with rapid climate change. Let's move ahead. How am I doing? Really? Okay, good. Okay. Okay, so let's go quickly to this world, because this world is really interesting for us. This is when the Mancos Shale around town was deposited, that gray stuff that sticks all over your bike tires. And incidentally, this is a reconstruction of the planet. This time you can see the planets are starting to break up. That light blue area is what was our part of Colorado. At this time, we cannot find any glacial deposits on the whole planet. And even when we go north to places like Alaska, we find broadleaf vegetation. So at this time, we think that we had, and again, we've got multiple proxies that show that we had carbon dioxide levels of around 1,000 to 1,500 parts per million in the atmosphere. And that resulted in very high sea levels, as you can see in this diagram. Now, some of the high sea levels in this diagram are because the continents were warped down because of continental collisions. So I'm not telling you that if we melted all the glaciers on Earth today, that Durango would go under. That's not the case. But we might have as much as 60 meters of sea level rise if you did melt Iceland and Antarctica. Right. Just hurry up here a little bit. So there's that diagram. Again, we're in this zone here of about 1,000 parts per million. The point of this paper that Breaker et al. Wrote was that with the emissions we are choosing to emit as a global society, we are headed for concentrations of around 800 to 1,000 parts per million. So as a geologist, when I hear that, there's a distinct oh shit, oh dear response. Just hurry up through this. So if you try to get to where we are now, that greenhouse broke down and the whole planet changed as a result of changing oceanic circulation and as a result perhaps of a lot of mountain building sequestering CO2 again. And that puts us into where we are now. And so here we've zoomed in on scales now from 65 million years of climate change to 650,000 years of climate change. And I want you to watch especially this peak in here. This is a proxy for temperature across here. The red line is CO2. And I added one thing to this graph, and that is the pre-industrial range of CO2 is this small red bar here. And where we are now is this large red bar. Mauna Loa measurements yesterday were 403 parts per million. So that is a huge departure from the 100 part per million variation we've had for the last several million years, and certainly for the last 650,000 years. And we may literally be playing with fire. We are in Sonoma. Okay, so Kevin showed you this graph. I won't linger on it, but I want to point out that you have seen data in this talk that shows you for the last 400 million years, changes in CO2 have been correlated with changes in temperature. And certainly that is the case now, and as well as other greenhouse gases. So That's resulting in ice loss around the planet. And if you look at ice water that's not stored on continents is stored in the ocean or in the atmosphere, as we've heard. And this top graph shows the top curve is showing what's going on with changing sea level. And one thing that you might not realize about rising sea level is some of that's meltwater, and that's probably what you expect. The other thing is that as you heat up the oceans, they expand. And so these two curves together here from expansion and meltwater give you that combined amount of sea level rise that we're getting. The bottom graph shows how much increase in sea surface height we've had since 1993. You can see it's focused in areas where, as Kevin was talking about, where the warm water piles up because the warm water is less dense. And so you're seeing that 40-inch difference across the South Pacific. Kevin told you about a little bit earlier. Also, the middle graph shows you how much sea level we would expect with the blue curve if we didn't have anthropogenic influence. The red shows what the model predicts, and this is really frightening. What we're seeing is even higher than we predict with models. So, 2 minutes. 2 minutes? Okay. This graph with the bar graph shows you an interesting reference for what happened in Earth's past 125,000 years ago. And that is this point on this paleo curve here. And sea levels were certainly 6 meters higher, perhaps as much as 9 meters higher. It gets hard to tell because the continents have moved just a little bit in that time. So we know that sea level was that much higher, and if you look at the concentration of CO2 at that time, you can see that that's the little green dot on this graph. It's just below 300. So how long will it take our planet to reach an equilibrium like it did at 125,000 years ago? Will we be on that trajectory? From studying the past, it seems like it. So most of the climate models you'll see talk about what's going to happen in 2100. As someone who studies deep time, I think beyond 2100. And I just can't buy any real estate in Florida at the moment. Okay, so here we go. A rich record of climate change on Earth. And we saw that there are icehouse and greenhouse worlds. A salient point about that is that it looks like the greenhouse gas concentrations during an ice-free world are like those that are projected under the most pessimistic scenario, and that's what our country seems to be, if not the whole world, embracing as a trajectory. The other thing, is it okay? Well, it's okay if you're a bacteria, but it might not be awesome to live through. It wasn't for about 90% of the species at the biggest extinction in the planet in the history of the Earth. And then finally, when you think about sea level change, remember that there's new water added from glaciers melting, and there's also a rise due to thermal expansion. There are more complexities as well, but we won't go into those. So thanks a bunch.
Yeah, I think if it's all right, we'll hold questions until the panel is up here, and then you'll have your chance to go into deep time. So our next speaker is Dr. Emile Elias. She's the director of the USDA Southwest Climate Hub. She holds a master's degree in watershed science from Colorado State University and a PhD in hydrology from Auburn. She is a research hydrologist, and her research interests include land use and climate change impacts on hydrology and water quality. Emile collaborates with partners to study and report on the impacts of regional changes on water resources, agriculture, and interconnected communities reliant on these resources. She publishes in peer-reviewed scientific journals, developing tools for informed decision-making and managing science synthesis projects. She has reported on the impacts of climate change on snowmelt runoff in western streams and cumulative impact of these changes. and she is one of the authors of the Southwestern chapter of the 4th National Climate Assessment. So, Emily.
I like that. Okay. All right, can you hear me okay in the back of the room? No, okay. How about now? Better? Okay. All right, well, good afternoon. Thank you for being here. Some researchers from Harvard published earlier this year a paper on climate change and mental health. And what they found was when you hear stories, like the stories you've just heard from the last 3 presenters, like what I'll be talking about today, that people generally feel more stress, more anxiety, and more depression, right? They do. So I'm here to say, before I start my talk, that I believe, having done this work for a while, that we're creative enough and that we're smart enough if we engage in some community action around both adaptation and mitigation, we can reduce some of the impacts that you've seen so far today. Not all of them, some of them. And so this is my call to action. I'm the 4th speaker. You might be getting tired. Your mind might wander while I talk. If it does, I ask that you please take a moment to think about what you might be able to do personally. A small thing, a big thing. You could unplug your cell phone charger when you're not charging your phone. You could pick a tree in your yard and make note every year of when that tree blooms and become part of the National Phenology Network. You could talk to your great uncle at Thanksgiving about what they think about climate change, not trying to just sway them necessarily, but just to understand why people believe what they believe. So that's my call to action. Today I'll be talking about agriculture and water resources in a changing climate, and I'll be dispelling the 3rd climate change myth in our series from my other 2 colleagues. As Dr. Rotman said, I am the director of the USDA Southwest Climate Hub. We work across 6 states in the Southwest. We work with farmers and ranchers and foresters on adaptation and mitigation. So what's the confusion and what's the misconception? The misconception is that climate change is not bad. We sometimes hear that the impacts of climate change could be equally positive and negative. And I'll be talking about some positive impacts of climate change to agriculture today. But I hope that you'll take away 3 things from my talk today. Number 1, climate change is already occurring and we're feeling those impacts in agriculture, and that it's human caused. Number 2, that the negative impacts to agriculture and the environment strongly outweigh those possible benefits, particularly at the end of this century. And number 3, that the changes in temperature and precipitation and extreme events have already and will continue to challenge food production and security across the globe and the provision of freshwater resources. So I have 4 background slides, 4 things that I need to talk about before I talk about climate change. One is that the impacts of climate change that we see are at differing scales. We can consider a global scale. That's what we've talked about for the most part. Many organizations were set up to work at a regional scale. Mine was, and that's because agriculture varies across this country, and the impacts of climate change will vary across this country as well. And most of the adaptation, most of that important on-the-ground work happens at the local scale. Also, temporal scales matter. We're seeing and observing impacts now. We often talk about mid-century, and I'll also be talking about the end of the century. Another really important thing when we're talking about impacts is how we assess those. This is from the IPCC, and this is a framework for climate change solutions, but also for understanding climate change impacts. So what we're looking at here is exposure and sensitivity. Those come together to create a potential impact. I'm going to talk about cotton when I talk about this. Cotton is grown in southern Arizona. Cotton already grows in a very warm climate. However, our temperatures are increasing, and so it is exposed, there's exposure, is exposed to higher temperatures. However, cotton is a pretty resilient crop. It can handle some high temperatures, so that would decrease the potential impact. Of course, in southern Arizona, we can't grow cotton without irrigation. And that irrigation water confers an adaptive capacity on the cotton plant. How does it do that? Through some things that we've heard about before today, through evaporative cooling of that plant. You irrigate the plant, and it actually cools its canopy temperature, it cools itself, so it's much lower temperature than the surrounding ambient temperature. So if we remove that adaptive capacity, if we don't irrigate, of course cotton's going to be more vulnerable. I just spoke about outcome vulnerability, very specific biophysical impact. People who look at impacts are now trying to go more towards what we call contextual vulnerability. What that means is we're trying to look at other things. We understand that other things impact vulnerability. For example, if we're talking about cotton, it could be global markets, right? Global cotton prices. It could be the fact that if you don't have surface water, you'll have to spend money to pump groundwater to irrigate your cotton. So we're trying to think more on a contextual basis as a community to help with adaptation. My third background slide, the difference between weather and climate. We often talk about weather as what you see on the news, climate as the long-term 30-year or more averages. However, as we saw in the presentations earlier, a change in the frequency and duration and magnitude of extreme weather is one of the most important consequences of a warming climate. Separating the two conceptually leads to confusion. The fourth background piece, we've talked about this a bit, is the National Climate Assessment. This was authorized by Congress in 1990. We're on the fourth one. The first volume was published last week. That's called the Climate Science Special Report. The second volume, which is all about the impacts, will be published at the end of 2018. I bring this up because I want you to see all of the different sectors that are represented in this report that we're not able to talk about today. There's water and energy, land cover change, forests. We have seen and heard mentioned to today the huge increase in wildfires across the western part of our country and the globe. So I bring this up because I hope that if you're interested in this and you don't hear something about it today, you'll look for the fourth National Climate Assessment. So what's our challenge for agriculture? The challenge is feeding a global population expected to be over 11 billion people by the end of this century, while also trying to maintain the integrity of environmental and ecological systems in the face of climate change. It's a grand challenge. It's a lot that we have to do. Another way of putting it is that agriculture needs to produce more on the same amount of land while adapting to climate change and not causing a huge environmental disaster at the same time. So here are some of the specific impacts to agriculture. One is that climate change is very likely to affect global, regional, and local food security by disrupting many aspects of the food distribution system, from growth to provision to shipping. Climate risks to food security increase as the magnitude and rate of climate change increases. So if by some miracle we're able to stop the mean temperature increase at 2 degrees Celsius, then the impacts will be less than if we rise to 4 degrees Celsius. Accurately projecting climate change risks to food security requires consideration of other large-scale changes. One would be our ability to move food, the transportation sector. There are many other large-scale changes that need to be considered. Poor farmers in developing countries may be especially vulnerable. This is partially because of a lower adaptive capacity, if you think back to the IPCC diagram that I showed originally. Global average yields of the 4 most traded food crops are already currently stagnating or diminishing on nearly a quarter of their growing areas across the world. We're feeling these impacts. What I'm showing now is crop insurance payments from 2001 to 2016 across the US. These are annual payments in hundreds of millions of dollars. What I think is very interesting about this graph, one thing is that the yellow bar is showing drought and the impacts of drought. The sort of bar below that is showing the impacts of moisture and excess precipitation. Those two together consistently make up more than 50% of our annual crop insurance payments. It's also interesting to look at 2012 and what happened in that very severe warm year that previous speakers spoke about. And what the third thing I want to point out here is the failure of irrigation supply. It's a small light green area from 2012 to 2015. What that is us realizing for the first time what happened in the California drought. And so failure of irrigation supply isn't irrigation equipment. That's lack of water to supply the crops. We think that the impacts of climate change in the Southwest will be through water shortage. We actually saw it in our crop insurance payments. This is showing the increase in yield of maize in the Midwestern United States over time, mostly due to technological improvements, while at the same time showing some really important extreme weather impacts. You can see the impacts of drought on yield and also blight and flooding. So this is where it gets complicated. I said we'd talk about some benefits and some detrimental impacts. This is where it gets complicated. So the yields of corn and soybeans and wheat, those increase as temperatures increase to a certain level, and then they decline sharply. If crops are already grown near their thresholds, of course, they're more vulnerable. At the same time, this increase in temperature could create a longer growing season. We have already seen a longer growing season of up to 20 days across the globe. In certain places, you might be able to grow multiple crops. That could increase yields, that could increase decomposition, that could make nutrients more available. At the same time, those increased temperatures can then shorten the grain filling period and so ultimately diminish yield. So I'm going up and down here. Benefits, pros, cons, pros, cons. A really important thing to note is the increased probability of heat waves, which of course could decimate a crop. Ultimately, what's the bottom line? Climate change will likely reduce crop yield potential, especially in certain regions, mid-latitude regions and tropical countries, particularly by the end of the century. I'm going to take a minute with this graph because I think it's very important. What you can see here is the percentage of yield projections. Closest to the origin, you'll see 2010 to 2029. That's where we are now. Most of the projections show an increase in yield for about half, 50% of the projections, that's seen in the blue, and a decrease in yield for the other half, that's seen in the mustard yellow color. The next 20-year period, each of these bar graphs, each of these coupled bar graphs represents 20 years. The next 20-year period shows 75% of the projections showing a decrease in crop yield globally, whereas 25 show an increase. And then by the end of the century, you'll see about nearly 80% of the model yield projections show a decline in crop yields. This all is occurring during really rapidly rising crop demand, which is important to remember. Perennial crops, a different type of crop, these are stone fruits, nuts. They have a winter chilling requirement. They need a certain amount of cold each winter. If they don't get that, those yields will decline if they can't reach those hours. This is especially important for, let's say, almonds in California. There's been a huge rise in almond plants area in California. It takes about 5 years for those crops to be viable, and generally you think you're going to have them for 30 years or more. But if temperature is increasing at the rate that we think it is, this could be very detrimental to the people growing those crops. Another challenge could be midwinter warming, which would lead to early bud burst and the decimation of that crop as well. Increase in carbon dioxide can actually be a benefit to plant growth. People mentioned this before, and they can also decrease soil water use rates. At the same time, increasing carbon dioxide can affect both grain and fruit yield and quality by reducing nitrogen and protein content. That could have some nutritional implications. And increasing carbon dioxide can disproportionately stimulate the growth of weeds. That's important for rangeland as well as cropland. So what does that mean? Here's the bottom line for carbon dioxide. This is at the end of the century again. Changes in maize yield. If you're looking at the yellow area, that means it's reducing. So through much of the equatorial region, through much of the mid-latitudes, you can see a decrease in maize yield by the end of the century, whereas in other areas, there's a potential increase. Could we move all the maize production there? Maybe. But then that creates a challenge for moving that corn to where it needs to be used. So there are compounding challenges here. Agriculture, of course, uses the most fresh water of any industry, any area. So changes to the hydrologic cycle are important. Higher temperature increases evaporation from both the land and water surface. That warmer air, as we've heard, can hold more water vapor, and that leads to more intense rainstorms. Those intense rainstorms don't infiltrate into the soil, they run off, and all of those factors combine to then increase the drought risk. You can see this pictorially here. The most important parts are near the bottom of this graph, at least for agriculture, and that is an increased demand for irrigation water with a change in climate, more frequent and longer periods of soil moisture deficit affecting crops, and also more pressure on groundwater components from a variable surface water supply. We also saw this during the California drought. It caused major changes to the aquifers in California. It caused land subsidence and disruption in pipes and irrigation canals. And it also caused the passage of the Safe Groundwater Management Act. So a lot of things happened because of those impacts. What we saw earlier is wet areas are getting wetter. Of course, for agriculture, that it can interfere with harvesting, planting. The intensity of rain can increase erosion, compound water quality problems, and globally increase flooding, particularly in lowland areas. Drier areas getting drier, of course, can be a major challenge for rain-fed agriculture, which currently produces about 60% of the world's food. So overall, the droughts will be more frequent and more severe, particularly in arid and semi-arid regions. From a global water resources perspective, that means that the fraction of the global population with water scarcity and affected by major river floods will increase by the end of this century. Climate change will also reduce renewable surface water and groundwater resources, especially in dry subtropical regions, which you can see here in yellow. So can we adapt? This is the real question. What can we do? We're working on things. A lot of different people around the world are working on improving plant performance, trying different measures to avoid pesticide damage, pathogen damage, reducing food waste. We're working on better forecasting, particularly for agriculture. The near-term forecasting is important, different management options, trying different things related to crop mix, changes in irrigation, tillage practices, and then of course improving soil quality is very important because that increases the organic matter in the soil and also the water holding capacity. What I'm showing here in the corner is an image of the greenhouses of Almeria, Spain. Has anyone heard of this area? Show of hands. Okay, a few people. Okay, so this is a huge area that produces more than 50% of Europe's fresh produce. It's about 165 square miles. You can see it from space. It is a sea of plastic greenhouses. I'm not advocating for this. There are some human rights issues associated with what's going on there, some environmental issues associated. But what I guess I'm trying to say is that we control our environment when we can and when we need to, even if there are detrimental consequences and people might go this direction, given the rapid temperature increases. So to summarize, moderate warming and more carbon dioxide could be good for plants, could help them grow faster. However, by the end of the century, severe warming and floods and droughts will likely reduce yields. A global temperature increase of approximately 4 degrees Celsius or more, combined with increasing food demand, could pose a really large risk for global food security. Didn't mention this, but livestock can be at risk from different pathways, one being direct heat stress and one being reduction in quality and quantity of their food supply. And the impacts of increased temperatures on both soil moisture, evapotranspiration, and evaporation, of course, reduce water availability, and that can increase agricultural vulnerability globally. Evaluating these impacts is complex, right? There are different scales, spatially and temporally. There are different types of vulnerability that can lead to some of the confusion. The impacts to agriculture and water resources are generally negative, and they can be very severe. We're already seeing some of those. That includes crop failure and prolonged drought. However, with mitigation and adaptation and some creative collective solutions, we might be able to minimize some of the negative impacts that I've talked about today. So if you have any questions, please feel free to email me. I will try to respond. These are the documents that I relied on for this. I'd be glad to send them to you if you're interested. Thank you.